Hello friends. In the previous few lectures we have been considering actual loading condition, and we have been attempting to arrive at the different stress components that are required to describe such a generalized stress condition. So when we say generalized stress condition, what it essentially means is that these stress conditions need not be uniaxial, they need not be biaxial, so they can be triaxial, and in addition to that they need not be inclined or oriented along the axes of our frame of reference. So generally when we consider the experimental condition or the test condition, our loading direction are along the axes of the frame of reference or the coordinate system. However, in actual cases, in the real life condition, it is rarely the case, and therefore we are forced to look into or describe the mechanical condition and material experiences in a given application or in a given real life situation. So therefore we have been spending some time in order to gain an understanding of how we can describe the mechanical condition experienced by a material in a real life situation. So what primarily distinguishes the loading condition is the direction along which the load is being imposed. Now, even though the direction along which the load is being imposed might vary, it might be tilted, it might have a specific angle associated with it, by defining or by quantifying or measuring that specific angle, we have been able to translate this inclined loading condition to the stress components that are rather relatable to us. So when we define the stress, be it normal stress, be it tensile stress, compressive stress or shear stress, we have a conventional description for it. We have a textbook rather, or a test description for it, wherein the loading conditions are aligned along the axis of the frame of reference or the coordinate system. So therefore what we have essentially done is from or based on the actual loading condition. So even though we have an actual loading condition which is quite different from what we have used to describe the tensile, compressive or shear stress condition, however what we did is we rather broke down this actual loading conditions into components of stresses that are quite relatable to us. The components of stresses which can be related to or which are similar to the test stresses that we have studied. So what essentially we have done is, in order to make or in order to describe this actual loading condition, we have dissociated this into components of stresses, and these components of stresses now are relatable to us, and they are relatable to us because we have dissociated them into normal and shear stresses, and these normal and shear stresses have a meaning that are rather similar to what we consider in a test conditions. So in case of normal stresses, what the characterizing feature of a normal stress is that it is perpendicular to our region of interest. The characterizing feature of the shear stresses, it is along the region of interest, along the surface of our region of interest. Even though actual condition is not the case, we have been able to describe this actual condition using this combination of these components of stresses. Using these components of stresses, we have been able to describe the actual stresses, so that using our fundamental understanding, now it is possible for us to describe any loading condition. When you know what a normal stress is, when you know what a tensile stress is, when you know how to define a normal stress, or when you know how to define a tensile stress or a compressive stress, and also how to define a shear stress, then using the combination of these two, we will be able to describe any loading condition. This loading condition can be biaxial, triaxial, uniaxial. It can be inclined in any direction, but since it is possible for us to dissociate this loading condition into several different components, and these several different components are either normal or shear. So using our fundamental understanding of these definitions of these normal and shear stresses, we are now in a position to describe any actual loading condition. Now in the previous lecture we saw that when you consider the most generalized case of triaxial loading, so when you consider a generalized case of triaxial loading, this could be tensile, or this could be compressive, or this could be combination of tensile and compressive, any combination of tensile and compressive. So, and this loading condition involving triaxial load comprises, in order to describe it comprehensively, in order to describe this loading condition exhaustively, completely, we need to have 9 components of stresses. So these 9 components of stresses include 3 normal stresses and 6 shear stresses. So this is something that we saw in our previous lecture. Now, towards the end of the previous lecture, we began considering what allows us to include both or include compressive stress as well in this loading condition, even though our discussion began exclusively with triaxial tensile loading. So when we began our discussion, when we began deriving or when we began looking into what are the different stress components that are required to describe the triaxial loading condition, we exclusively focused on tensile loading alone. But now, in the generalized case, we can also state that it is also possible for us to include, or the triaxial stress to include compressive loading, and it will be easy, or it will be possible for us to describe the components of stresses wherein we have the combination of tensile and compressive, and also compressive loading alone. The reason it is possible, even though we started off purely or exclusively with tensile loading condition, even though it is, or the reason it is possible for us to include the compressive loading is because we have appropriate convention to distinguish the tensile from compressive loading. So when you introduce such convention, then it becomes rather straightforward for us to describe the triaxial compressive loading or the triaxial combination of tensile and compressive loading using the components that we have arrived at for purely tensile case. So even though we have largely focused on the purely tensile case, when you incorporate the appropriate convention, it becomes possible for us to describe or to include the compressive stress as well. Now, this convention then plays a critical role in order to have a generalized understanding of the different stress components that a system experiences. So, but in addition to the normal stresses, which can be categorized as tensile and compressive, we also have this shear components. And so far, we have not considered extensively on what are the different conventions associated with these shear stresses. So we have seen the convention associated with tensile and compressive stress, meaning when you have tensile stress, it should be a positive, and a compressive stress should be denoted by a negative sign. So correspondingly, when you have a stress component with a negative sign, it essentially means that this stress component is it emerges from a compressive load. So therefore, it is possible for us to have a generalized description of the loading condition. So when you have a generalized loading condition which involves combination of tensile and compressive, then it becomes possible for us to relate or to arrive at the different stress components, and it is also possible for us to understand what are these different stress components involved. What are the different stress components? Are they either tensile components, or are they compressive components? So these are possible because of conventions, but such conventions we have not considered for the shear stress conditions. Now when you look into the shear stresses that form the components of the stresses, they are typically of this form, that is tau. So one of the example is tau xy. So what this shear component means is that this particular stress is acting along the x plane, or acting on the x plane and along the y direction. So typically, when you consider the components of stresses, these components of stresses, they involve normal and shear, and the shear are represented in this manner, and the first subscript, it represents the plane on which the shear stress is acting, and the second subscript is the direction. And since we just have two subscript describing the shear component of the stress, it becomes possible for us to describe all the combination, the different combination, or to gain an understanding of the convention associated with the shear stress by just considering a two-dimensional plane, a two-coordinate axis system. So instead of considering an actual three-dimensional coordinate system, it is possible for us, since the shear stress is associated with just two subscripts, that is all we need is an understanding of on which plane it is acting and along which direction it is acting. So therefore, we can gain the understanding of the convention associated with the shear stress using just two coordinate systems, or two axes of a coordinate system. Now, if we assume this axis to be x and this axis to be y, we have seen that the way we designate a plane, particularly while we are discussing the components of stresses, is we consider a plane or we designate a plane to a specific axis if it cuts that specific axis. Now if you consider a plane such as this, let me draw a simpler one. If you consider a plane such as this, and this plane cuts the y-axis, so therefore what happens is that this would be referred to as the y-plane. And in the same way, this plane also cuts the y-axis, so this plane will also be referred to as the y-plane. On the other hand, we have two other planes that cuts the x-axis. Therefore, these planes are referred to as the x-plane. The reason we have this specific designation is because if we refer to this as in three-dimensional case, if we refer to this as by the planes that are, or the axis to which these planes are parallel, then we need to have two subscripts. So generally, even though it's a convention or it's in the general case, the planes are rather described based on the axis to which it is parallel. The reason we chose the other way, we chose to designate the plane based on the coordinate axis it cuts, is because it reduces the number of subscripts that we need to describe it. So therefore, in this case, what we have is this plane here, the one in red is y-plane and the one in blue is the x-plane. So correspondingly, this stress here, this shear stress here can be represented as tau yx, because the shear stress is acting on the y-plane along the x direction. And in the same way, this shear stress can be expressed as tau yx. In the similar way, the shear stress would be tau yx, and the shear stress also would be tau yx. So what essentially we have is a plane and the direction combination. Now this shear stress would be tau xy, and this shear stress would be tau xy, and similarly we have similar identical designations for these shear stresses as well. All these have the represented by tau xy. Now we saw that this simple stress square, so this representation of the different planes in two-dimensional system or in a two-dimensional coordinate system, particularly with a purpose to understand the convention associated with the shear stress, this are referred to as the shear square or stress square. Now in this shear square or the stress square, these are essentially the part of the element of our sample. So we have a sample, and we have considered, in the previous discussion we have considered a three-dimensional element. So this three-dimensional element helps us understand what is the orientation, what is the inclination, along which direction was each of these components of stresses were aligned. Now in this case, since we are largely interested in understanding the convention associated with the shear stress, we are considering as just a two-dimensional representation of the element of a sample that is experiencing the loading condition that we impose on it. So since it is a part of an actual sample, this is a segment, this is an element of an actual sample, therefore it needs to be, we need to ensure that this sample is stable, particularly it is rotationally stable, or it exhibits a rotational stability. So because of the loading condition, this element alone is not rotating. So essentially we are imposing tensile or compressive loading. So therefore, as a result of it, there can be expansion or compression. Very rarely we experience a rotation of an individual element within the sample. So therefore, there needs to be a rotational stability associated with this element. So that means the stresses that are acting on these corners needs to be balanced. If they are not balanced, there will be a resulting rotation. So if these are not balanced, supposing if the stress in blue is greater than the stress in red, there will be a rotation in this direction. So therefore, there needs to be a balance in these stresses. So ultimately, this rotational stability, it helps us reach a relation that is tau yx is equal to tau xy. So this is something that we saw at the end, towards the end of our previous lecture, that is tau xy is tau yx. Now let us see if this relation, that is what this relation means is the shear component of the stress acting in the y direction or acting on the y plane along the x direction. So acting on the y plane along the x direction is equal to the shear stress acting on the x plane along the y direction. What it means, again, what this relation it indicates is the shear stress acting on the surface of the y plane along the x direction is equal to the shear stress acting on the surface of the x plane along the y direction. Now let us revisit our consideration of the elements or the three-dimensional element that we consider in order to understand the components of stresses. So this is the three-dimensional element that we considered to understand the components of stresses. And if we superimpose the coordinate system, then this would be our x-axis, this would be our y-axis, and this would be our z-axis. So what we have done is consider the element of a sample that is experiencing a triaxial loading condition, and we have superimposed our coordinate system onto it. Now this would be the normal stress along the x direction, and there will be two components of shear stress associated with it. So therefore one component of the shear stress will be in this direction, and also the other components of the shear stress will be in this direction. So this would be sigma x, this would be tau xz, and this would be tau xy. So the tau xy is the shear stress that is acting on the surface of the x along the y direction. So we have tau xy here. Now here we have similar stress that is acting, stress components that are similar stress components acting on this y surface here. So therefore we would have our sigma y, that is the normal stress that is acting perpendicular to the y plane. We will have two components of the shear stress, that is tau yz and tau yx. So these are the two components, that is tau yx and tau xy. These are the two components that are being mentioned here. Now what this relation states is these two stress components, that is tau yx, tau xy, these shear stress acting on the plane, acting on this plane, on the y plane in the x direction, is equal to the shear stress acting on the x plane along the y direction. So both these are equal. Now when you compare these two shear stresses in, so this relation we have arrived from the stress square. We have considered a special condition, a special case, and then we have arrived at this relation. Now when we will try to understand if this relation is applicable to the actual case. So this is the actual generalized case where we have a sample experiencing triaxial loading, and we have considered an element of the sample, and we have considered the different components of the stresses associated with that sample, and now we see these are the red arrows are the true stress components that are equated in this relation. Now again, when there is an imbalance between these two these two stresses, components of stresses that are indicated in red, now there will be a rotation. Again, the rotation stability will be disturbed. Supposing this tau xy is greater than tau yx, then what it means is that the system would start to rotate, or this element would start to rotate in this direction. So therefore again, this element is an actual part of a sample experiencing a triaxial loading. So this triaxial loading can be compressive or tensile or combination of these two. So therefore we seldom observe the rotation of any elements. So there is a rotation stability associated with it, and this rotation stability in an actual sample is again ensured by this relation here. So therefore this relation that we arrived using the stress square is applicable, or it can be verified by considering the actual case wherein we have the system experiencing a triaxial loading condition, and by considering these relation in this actual element, in this part of the actual sample experiencing the triaxial loading condition, we are able to verify that this relation holds true. So what is the significance of this relation? That is, when you have such a relation, that is yx is equal to xy, that is, to put it, when you consider completely in a numerical perspective, when you haven't taken a numerical perspective, what it essentially means that even though we interchange the subscripts, the value of the components of the value of the stress is going to remain the same. The value of this parameter is going to remain the same. This is a purely a numerical perspective without considering any physical attributes of what these individual parameters mean. When you just say that when you interchange the subscript associated with this parameter tau, the value of this particular parameter, the entire parameter, remains the same. When you consider the physical significance of it, when you have a combination of a plane on which the shear stress is acting and the direction along which the shear stress is acting, and when you interchange the plane to the direction and direction to the plane, the value of the shear stress is going to the same. So this is the physical understanding of what this relation means. So this relation here is a generalized one and can be extended to any combinations of plane and direction. So when you have a plane and a specific direction along with the shear stresses acting, and then the direction and plane are reversed, the value is going to remain the same. So therefore this can be extended to not only y plane and x direction, it can be extended to y plane and z direction. So we have a relation such as this. In addition to this, it can be extended to x plane and z direction. So therefore we have this relation as well. So the rotational stability yields us all these three relations, which means the shear stress, when we interchange the plane and the direction, the value of it is going to remain the same. Now this shear stress can be, or this relation or this equality between the combination, the couple of shear stress, can be related to the components of stresses that are required for us to describe the generalized triaxial loading condition. So when we consider the generalized triaxial loading condition, the stresses that are required, the components of stresses that are required to describe it, can be expressed in the form of a matrix wherein we have the normal stress associated with the x-axis, the shear stress acting along the x-axis in y direction, the shear stress acting along the x-axis in the z direction. Then we have the shear stress acting along the y-axis in the z direction, the normal stress perpendicular or along the y-axis, then the shear stress acting along the y-axis in the z direction, and the shear stress acting along the or on the z plane in the x direction, the shear stress acting along the z plane in the y direction, and the normal stress, the particular component of the normal stress. Now this essentially shows that we need 9 components of stresses to describe any triaxial loading condition, be it compressive, tensile, combination of these two in any inclined plane. Now when you introduce this relation here, this entire matrix can be, when you introduce this relation here, this entire matrix can be written as sigma x, tau xy, tau xz. And now since tau yx is equal to xy, then this can be replaced. So this can be replaced as tau xy, and we go back to our sigma y, and the similar way we will let this remain the same. And when you consider the third row, there is tau zx, which is equal to xz. So therefore we can represent this as xz. And in the same way we have yz, and this term should be tau zy, but this is similar to tau yz, so therefore it can be represented by tau yz. And finally we have sigma z. So all the entities in the red, they are duplicates. So we have tau xy here, tau yz here, and tau xz and tau xz here, tau yz and tau yz here. So all these terms in the red are the duplicates. So essentially then in this case, what we need to describe a triaxial loading condition is just 6 components of stress. So what we have then, we began with a triaxial loading condition. Inclination, the loading can be inclined in any angle, and it can be compressive, tensile, or combination of these two. And so far the previous understanding was such that we need 9 components to describe this loading condition. When we have a generalized loading condition, we don't know it is uniaxial, biaxial, or triaxial, or in which angle it is oriented, but if you want to describe it, to make any sense out of this loading condition, we saw that we need 9 components of stresses. But when we look closely into the shear stresses that are involved in these components of stresses, the shear stresses that are experienced by these sample, particularly the elements of the sample, and we ensure that the rotational stability, we ensure the rotational stability of these elements, then we see that there are duplicates associated with it, and therefore all that we need is, instead of 9, we now need just 6 components of stresses. So instead of having to describe 9 different components of stresses, now we have to just describe 6 different components of stresses. So what this essentially means, even though in order to complete this matrix, in order to give a comprehensive understanding description of the triaxial loading condition, even though we need 6 components, of course it includes duplicates as well, but we need 9 components when we include the duplicates as well, and 9 individual entities. When you look closely, all that we need is 6 independent components. The reason we see or include this independent is the term independent is because these two are rather duplicates, meaning they are dependent on one another. So all that we need is we need 6 independent components. So when the question is how many stress components that we need to describe a generalized loading condition, then the answer is essentially 9 components. But how many independent we need? It is 6. The difference is that when you consider the independent components, these are essentially what you need to find. But when you want to fill the entire matrix, you need 9 components. But essentially how much you need to find in order to fill this matrix is just 6 components. So I hope you are able to distinguish the difference between filling the entire matrix, needing the entire components of stress, and finding and to know how much we need to fill the entire matrix. So since we are able to establish this equivalency, this relation between these different shear stresses, all we need to find out is 6 independent component stresses. However, to fill the entire matrix, we need 9 components of stresses. 6 independent and totally 9 components of stresses. And of course, this 9, it involves or it includes the dependent components as well. So even though we need to fill the 9 entities, all we need to find out is fill and find out. All we need to find out is just 6 independent components. Now, even though the consideration of our stress square allows us to find out this equivalency, there is also another potential problem with the stress square. So the stress square, by considering in order to introduce or in order to ensure the rotational stability, has allowed us to introduce a specific condition or specific relation. There is rather an issue associated with this stress square if you look closely. Of course, you might have figured out right now what it is. So if we designate the stress as tau y, so this is the y-axis and this is the x-axis. If you designate this as tau yx, and this stress is also tau yx because it is also arcing along the y-axis in the x direction, we have a way of the parameter or the terminology that we use to represent, the way we represent these two stresses are the same, that is both are represented by tau yx. However, when you look closely into the direction, these are acting in the opposite direction. So even though the value assumed by or the parameter that we use is identical, when you look closely and consider the direction, they are acting in the two different directions. This particular stress, even though we use the same term or we use the same parameter, these are acting in two different directions. So therefore, we need to distinguish one stress from another. We need to distinguish these two stresses, one acting in this direction from the another that is acting in completely opposite direction. So how can we do that? So this is where the convention associated with the shear stress comes into play. Now for the case of the stress square, let us consider all the shear stresses that we were able to introduce in this stress square. So if you consider here, we were able to introduce all the close to 8 shear stresses within this stress square. So using the stress square, we were able to introduce 8 shear stresses. So here, so far we have introduced 2. So this will be acting along the x plane in the y direction, and this is also the shear stress that is acting along or on the x plane along the y direction. So this shear stress here is also acting on the x plane along the y direction. So this shear stress is also acting on the x plane along y direction. So this shear stress here is acting along or on the x plane along the x direction, and this shear stress is acting on the y plane along the x direction. So what essentially we have is we have 8 different components of shear stresses that are included in this stress square representation. Now let us consider each of these stresses individually. So let us designate this as 1. So designate this as 1. So this 1, the first shear stress that we are considering is tau x, or rather tau yx. Now when you consider the plane on which it is acting and the direction on which it is acting, so this is your x plane and this is your y plane, and this plane here, it cuts, rather let me use a different color, this plane here, the plane in red, it cuts the y-axis in the positive side. So So this plane that I have highlighted in red, it cuts the y-axis in the positive plane. So therefore, this stress can be written as y plus. I am including the plus to indicate that this stress, it cuts the y plane along the, or rather this stress is acting on a plane that cuts the y-axis in the positive side of this coordinate axis. So it is cutting the, so this is the positive side and this is the negative side and so on. So this is the positive side and this is the negative side. So the plane that we are interested in is cutting the positive side of the y-axis, and the direction x along which the stress is acting is also positive. So what essentially we are attempting to do is, we are attempting to distinguish these 8 different stresses. So all these 8 different stresses are being represented by just 2 subscripts. So we are trying to distinguish these 8 different stresses. So now we are able to distinguish, or we were able to give an appropriate representation for the stress N1. Now let us consider the stress N2. Stress N2. The stress 2 is again acting on a plane that cuts the x-axis in the positive region. So in the positive side of the x-axis, this green plane is cutting. So the stress is acting on a plane that cuts the x-axis in the positive region. So therefore, the stress 2, that is xy, can be written as tau. It is cutting the x plane in the positive region, and the stress is acting along the positive y direction. Now the same understanding or the same representation, the way of representation can be extended to 3. The stress 3 is acting, it is also represented by xy. However, the stress 3, even though it is acting on the same plane, that is positive x plane, the direction along which it is acting is negative y direction. So if you consider this stress is acting along the negative y direction. The stress here is acting along the negative y direction. So therefore it is y minus. Now let us consider the 4th component of the stress that is included in the stress square, the 4th component. So this 4th component can be represented by, so this 4th component, it cuts this plane on which this 4th component is acting. So 4th component is this one. The plane on which this 4th component is acting, this plane, it cuts the y-axis in the negative quadrant. It cuts the y-axis in the negative side. So therefore it will be y minus, and it is acting in the positive direction of the x. This x, it is acting in the positive direction of the x. The stress is acting in the positive direction of the x. Therefore it is x plus. Now let us go to this stress here, stress designated as phi, and this stress, then again this stress is acting on the plane that cuts in the negative side of the y-axis. So therefore y minus, and the stress is acting along the negative of the x-axis. It is acting in this direction. So it is along the negative of the x-axis. It is along the negative of the x-axis. So x minus. Now let us consider the 6th stress here. The 6th stress here. When you consider the 6th stress, this stress is, again this stress is acting in the plane that cuts the x-axis in the negative quadrant. So therefore it is x minus, and it is acting in the direction that is to the negative of the y-axis. So it is acting in the direction that is negative to the y-axis. So therefore y minus. And finally we have our 7th stress that is acting in the same plane. So therefore, so the 7th stress is this one, and it is acting on the same plane that cuts the x-axis in the negative side. So therefore we have tau x minus. So these two stresses are acting on the same plane, so therefore tau x minus, but here the direction is along the positive y, so therefore y plus. And finally this stress, that is 8, the 8th stress is, again it is acting on the positive y plane, so y plus, but the direction of x is negative. It is acting in the negative x direction. So what essentially we have done is, we have now used appropriate notation to include the difference in the direction associated with the shear stress. When we just have two subscripts, we were not able to rather distinguish the different shear stresses, those acting in the different directions and those acting in the different planes. So the stresses acting in these two planes, they have had same description. So in this stress, so stresses 1, 4, 5, 8, they all had the same description. Stresses 1, 4, 5, 8, they all had the same description, and all the other stresses as well, they had the same description. But now what we essentially did is, we were able to, using positive and negative signs, using the sections in which these planes, they rather intersected or they crossed the coordinate system, and also the direction, positive and negative direction along which the shear stress were oriented, we were able to distinguish these different stresses. And now what we essentially have is, we have 8 unique representations for these different stresses. Now the convention we have to distinguish these stresses are that when the signs of these coordinates are similar, then these stresses are considered to be positive. So in this case, we have similar signs. We have y plus and x plus. In this case, we also have similar signs. So we have y plus and x plus. So here plus and here plus. The same way, in this case, we have x plus and y plus. So therefore, these two belong to the same category. And here we have y minus and x minus. So this belongs to the same category because we have identical signs. So here plus plus, plus plus, and here minus minus. So identical sign. So the same way, this also belongs to the same category. When the signs assumed by the subscripts are identical, then these stresses are positive. So the way we distinguish a positive shear stress from the negative shear stress is that when the signs associated with the stresses are identical, then we refer to that as the positive shear stress. So in this case, we have plus plus, plus plus, and we have minus minus and minus minus. In 1, 2, 5, 6, we have plus. So identical signs. So therefore, we have a positive shear stresses. On the other hand, when we have rather unequal or dissimilar signs, plus minus, minus plus, and so on and so forth. So we have, these are the subscripts with dissimilar signs, then those we refer to as the negative shear stresses. Now what essentially we have been able to do is, we have been able to distinguish the positive shear stress from the negative shear stress within or using the stress square here. So therefore, when you consider the stress square, which includes a 2 axis, so this is positive, negative, negative. So this is our x-axis and this is our y-axis. Then there are certain stresses that are positive. So these stresses are positive. The one represented in red are positive because these are acting on the y-plane, on the positive y-plane in the positive x direction. And in the same way, these stresses are also positive because these are acting on the positive x plane in the positive y direction. And similarly, these two stresses are also positive because they are acting on the negative y plane in the negative y direction, and this stress is acting in the negative x plane in the negative y direction. So we have similarity in the signs. So these two are represented by plus plus signs and these two are represented by minus minus. So these are positive stresses. On the other hand, these two are, or these four are the negative shear stresses. So because these are associated with, so this one is acting, so this one here is acting in the negative x plane but along the positive y. So we have the combination of minus plus, and this stresses, these are acting on the negative x plane but along the positive or negative y plane but along the positive x direction. So there are dissimilarity in these symbols. So therefore, these are negative stresses and the ones in red are the positive stresses. So what essentially then we have arrived at is, we have now a relation that is established between the shear stresses, and also in addition to that we have now understood what is the convention associated with the shear stresses. So when we have shear stress that is experienced by a given element, a given sample, then we can use this representation here. When the combination, when the direction along with the plane, when they are part of the positive quadrant, so these are referred to as the different quadrants, when these are part of the completely positive quadrant or the completely negative quadrant, then those shear stresses, we refer to it as the positive shear stress. When they belong to the combination of positive and negative quadrants, we refer to them, or we refer to that as the negative, or we treat that as the negative shear stresses. So essentially, in addition to the equality relation between the different shear stresses, the stress square here also help us understand the convention associated with the shear components of the stresses. Now, what essentially we have been considering is, we have been considering the generalized loading condition, and from that the reason why we are considering the generalized loading condition. So generalized loading condition is, it includes triaxial loading, and this triaxial loading in any direction. So triaxial loading in any direction. So the reason why this is what we refer to as the generalized condition. Now the reason why we are considering this generalized condition is because from this we can describe the stress associated with, or from this we can describe. So using this as our starting point, we now have described, or we now have arrived at the components of stresses. So based on this components of stresses, now it becomes possible for us to describe any loading condition in any direction, be it unilateral, be it triaxial, or be it biaxial, be it tensile, or be it compressive, or combination. All this, it is possible because we have understanding of this generalized triaxial loading condition. We have an understanding of this generalized triaxial loading condition. Now from this generalized understanding, we can consider any other specific loading condition. So from this generalized understanding, we can use the generalized understanding to describe any specific loading condition. So this specific loading condition, some examples of the specific loading condition can be uniaxial tensile, or it can be also uniaxial compression, biaxial tensile, biaxial compression. You can have a uniaxial actual loading condition, uniaxial actual loading condition, or uniaxial test loading condition, biaxial actual, biaxial test. Irrespective of what the loading condition is, from this generalized understanding, we will be able to arrive at, or you will be able to describe the corresponding components of stresses, thereby enabling us to describe the mechanical condition experienced by the sample. Now, this generalized condition is not just confined to the loading condition alone. This generalized discussion, or the generalized understanding that we gained, is not confined to the loading condition alone. Meaning, so far we have considered the sample as a three-dimensional one. So therefore, from the three-dimensional understanding, it is also possible for us to describe what would be the components of stresses when we are considering a pseudo three-dimensional material. So let me repeat, we have a generalized understanding of describing any mechanical condition. So because we have already considered triaxial loading condition, so from that generalized understanding, we can talk about any specific condition. These specific condition, we have seen some examples. Now the discussion, this generality and the specific conditions, they need not be always associated with loading condition. It need not be often the specific condition means we have uniaxial or we have biaxial. It can also be that in the specific condition, we are not essentially considering a three-dimensional system, but rather a pseudo three-dimensional system. We are not considering a sample that is three-dimensional in nature, but rather pseudo three-dimensional in nature. So what I mean by pseudo three-dimensional is, so pseudo three-dimensional, pseudo meaning false, I believe you already know that. So what we mean by pseudo three-dimensional is that when you consider the application of, say, particularly metals and alloys, one of the critical application is that they form the body of our automobiles. So you can consider any automobile, say for instance car, or you can also consider the spacecraft. A major form in which the metals and alloys are being used is that they are used to rather form the, in addition to the frame, they are also used to form the body of these automobiles. So the way these metals and alloys are being used are in form of what we refer to as the sheet metals. So when you consider the build of the body of your automobile, the body of your spacecraft, when you consider the metal, the role of the metal that it plays, it is used to cover the frame of your automobile, the frame of your spacecraft. Now these frames are usually covered, or these frames are usually made of the sheet metals, and these sheet metals are not your typical three-dimensional material, and these are rather just a sheet which are of a pseudo three-dimensional in nature. So what in the subsequent lecture we will be considering is how the mechanical condition a material would experience when it is assumes a form of a sheet metal, when as opposed to a conventional three-dimensional case, for instance, rather a cylinder that we have so far been considering, when the metal of our interest, the material of our interest is of the form of a sheet metal. How would the mechanical condition experienced by the sheet metal would vary when compared to, so these sheet metals are nothing but sheets. So these are not typically a three-dimensional material, they can be treated as a two-dimensional material or similar to a pseudo three-dimensional one, and it means there could be a change in the mechanical condition experienced by a sheet metal when compared to the actual, say, a cylindrical metal or a cylindrical sample. So from this generalized understanding, let us see, or let us consider how the mechanical condition experienced by the sheet metal would vary. So this is what we will be considering in the subsequent lecture. Goodbye.